Welcome to the Organic Chemistry Bootcamp Session 1. In this session, we'll do a molecular overview. Now, on the one hand, this is material covered in organic chemistry, but on the other hand, this is really material that you should have learned and mastered in Gen Chem. Problem is, most students don't learn it well enough, and most students don't remember it. So we're going to kind of fly through it, but at the same time, keep in mind that I have a very full-length review on some of the material I'm going to fly through today on my website, laversci.com/Orgo Basics. And there's another one that I don't know the link offhand, but it's the Intro to Orgo video series. If you scroll down on the Orgo Basics page, there's a link to that, and that goes through the atom, the electrons, the shells, electron configuration. You definitely need to know that. But for the sake of what we need regarding the atom, what we need in organic chemistry, well, we need to know the basic structure of an atom. So when you think of an atom, what comes to mind? What does it look like? What are the particles? What are their charges, and where are they located? Now, a quick tip for those of you when you're watching the videos later, if you hear a question, pause the video, try to answer it, treat it like a live session, get that learning experience out of it, and then watch to make sure that you got it right. So the center of the atom, which is really, really tiny, is the nucleus. In the nucleus, we have protons, which I'll put as a P, and they are positive, and we have neutrons, which are neutral. They do not have a charge. The protons are the only thing in the atom that contributes positive charge. And protons, because they're trapped in the nucleus, do not move. Guys, remember this. Protons do not move. Protons don't attack. You never start an arrow at a proton because they're trapped in the nucleus. The next thing we have is the neutron. The neutron is neutral, and it doesn't really do anything in terms of reactions and mechanisms. It contributes to the mass of the atom, and it'll play a role in the stability of isotopes. But in terms of what a neutron does in a reaction mechanism, nothing. So don't worry about the neutrons unless you're trying to calculate the mass of an atom. And finally, surrounding the nucleus, we have the different orbitals or shells, and that's where the electrons are located. And you do have to understand the nature of the shells, the specific orbitals with the electrons. The electrons have a charge of -1, and the electrons that we specifically care about are the outermost electrons. What are they called? Valence electrons is absolutely correct. The valence electrons are sitting on the outside. They are the most easily accessible or the easiest to jump or to move. The valence electrons are the key behind your organic chemistry reactions. Anytime you show a bond forming, a bond breaking, an electron reaching out to attack something, it's the valence electrons that we're looking at. Now, in Gen Chem, you learned how to do electron configuration, and if you forgot it, that's why I gave you the link. Go back, review, understand the electron configuration. Let's take a look at something simple. Anyone know the electron configuration for carbon off the top of your head? And if you're not sure, carbon is atomic number 6. All right, so I'm seeing quite a few putting in the correct answer, which is 1s2, 2s2, 2p2. For those of you who didn't know it, your homework is to go back and review electron configuration. The pieces that we have here, anything that's not in the highest number is considered the kernel. That's inside. It's almost like it's part of the nucleus because you have the nucleus and the inner shell that are trapped. They're not doing anything. The outermost shell, specifically the outermost SNP, that is your valence shell. Now, the valence shell is governed by the octet rule, and the octet rule says an atom wants to have 8 electrons in its outermost shell. There are exceptions to the octet rule. If you are familiar with them, go ahead and type them in. I'll start them off. Exceptions to the octet rule. Firstly, octet, you see the word 8 in there. October used to be the 8th month before Julius and Augustus Caesar were honored with a month after them. An octagon has 8 sides, right? The octet rule is the rule of 8. A couple of exceptions you want to know. Hydrogen and helium are going to have a max of 2. That's because they only have an s orbital. Again, if you're not familiar with orbitals, go back and review. Then we have boron and aluminum can have 6 instead of 8. This is going to be key behind a lot of reactions like hydroboration and electrophilic aromatic substitution using aluminum, right? Lithium aluminum hydride for reduction, or AlCl3 for EAS. Part of the reactivity is the fact that they're okay with just 6 instead of 8. And then the opposite end of the spectrum is the larger atoms. The larger atoms can have 8+. For example, phosphorus, sulfur, chlorine. These are the ones that are sitting at level 3, n equals 3 on your periodic table or lower. And because they have a d orbital, they can expand beyond 8 and hold more electrons. Why is this important? This is going to lead into understanding about bonding. But this also leads into the idea of reactivity. If carbon wants to have 8 and it doesn't, it's going to try to interact with something else. If carbon has 8 and you steal something, carbon is now desperate for something else. So the octet rule is sort of the driving factor behind why atoms want to react. And if you can understand this, you won't have to memorize the mechanisms. It'll make sense. A lot of what we're going to look at requires an understanding of, well, it really requires a periodic table. But let's face it, if you're on an exam and you see the same atom over and over again, and you keep having to refer back to the periodic table, then A, the time it takes to sort of turn away from your exam to look up the table, you may lose your train of thought, and B, I know it's a few seconds here and there, but those are precious seconds wasted. In organic chemistry, you're pretty much going to see the same 10 atoms over and over again, maybe a few more. So I want you to memorize them. I want you to memorize these 10 atoms on the table as follows. In period number 1, we have hydrogen. Period number 2, CNOF. Period 3, under nitrogen, you have phosphorus. Under oxygen is sulfur, and then the halogens are chlorine, bromine, and iodine. If you have heard any of my videos, workshops, what do you always hear me say? Understand, don't memorize. This is one of the few times that I'm telling you memorize, 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 because you don't want to keep looking back to a periodic table if it's just these atoms that you need to see. The trends that come with them are electronegativity, which increases up and towards the right. So if you ever have to determine which one's more electronegative based on, say, acid-base strength, which we're going to look at later, you'll know it by memorization. Size goes down and towards the left. So again, if we're looking at trends, you'll know it. And then valence electrons, 1, 4, 5, 6, 7. The ones I mentioned as an exception to the octet rule, hydrogen is tiny. It's the first one. Phosphorus, sulfur, chlorine, and anything small below are bigger. And then boron and aluminum, which you don't have to memorize, they are sitting right over here. So because they have 3 valence electrons, they just want to pair them. They don't want to do much else. And you're going to see a couple of metals here, and that's pretty much it for organic chemistry. So let's go back and take a look at the next topic, which is hybridization. What is hybridization, and why do the atoms bother? Orbitals interacting is on the right track, but it's even more than that. It's the orbitals fusing, combining to form a brand new orbital made out of the 2 pieces that you started with. And I see sharing an electron cloud. It's like the carbon can be sp, sp2, or sp3. You are all absolutely correct. Let's go back to the electron configuration of carbon. Carbon is 1s2, 2s2, and 2p6. We said that 1s2 is in the kernel, we don't worry about that, and that the valence electrons are 2s2 and 2p6. If we try to draw it out, then we're going to see the s orbital, which is lower in energy, and the p orbital, which is higher in energy. There is 1s and 3p. Again, this is something you learned in Gen Chem, but you have to know it and understand it. The alphabet principle says that we start from low energy to high energy. So we put the 2 electrons in the S, that's low energy, and 2 electrons in P. We don't double them up. If there's the option to be spaced out, meaning if they can each have their own suborbital, they don't want to share. In order to make a bond, you need an atom with only 1 electron in an orbital and another atom with an electron in the orbital, and the 2 are going to overlap. So that works out really nicely for the p orbital. And for the p orbital, which means that carbon can have 2 bonds. So how on earth is a molecule like CH4 possible if CH4 clearly has 4 bonds to the carbon atom? You guys, that is 2p2, not 2p6. I naturally always want to go with a full octet, so I wrote 2p6 there. Okay, so the question is, how is it possible for carbon to form 4 bonds, like the CH4 molecule, if it only has 2 orbitals that are half empty, meaning 2 orbitals that are capable of forming a bond? And the answer is hybridization. For a bond to form, you need to have an orbital with 1 electron capable of fusing with another one. So we need to find a way to get S to contribute its electron to separate its 2 electrons so that 1 will be in that S and 1 will be in that empty spot. So here's what's going to happen. We give S a boost of energy. It doesn't want to let me highlight that. Let's try that again. So if this is S, which is lower in energy, we give it a boost of energy. I don't know why it doesn't want to do that, so we're just going to rewrite it. We give it a boost of energy so that it is now the same level as P. These are called degenerate orbitals. What does degenerate mean? It means they're at the same energy. And if they're at the same energy, does S want to have 2 electrons, or does this one want to jump over to the empty orbital? Well, if the 2 are in a lower energy state and they're paired, that's fine. That's the idea. They want to be together. But if you raise it up to the same level as something else, and suddenly at the very same level you have an empty orbital, the electron is going to move over. The way I like to think of this is sharing a room with a sibling. I have a younger sister, and when we were younger, we lived in an apartment that had a small number of bedrooms, so my sister and I would share a room. It was natural. We had a brother, he gets his own room, and the 2 girls are sharing a room. But then years later, we moved into an apartment that had an extra room. Was I going to share with my sister, or say that if there's an extra room, I'm going to have my own room and she'll have her own room? Because if there's the space, why would we want to crowd each other? Why would we want to share if we could each have our own room? And that's exactly what's happening here. When there is no choice, then the 2 electrons are paired. But when there's an empty room, then the 2 electrons that are together will separate. So what do we have now? We now have 4 degenerate orbitals, each with 1 electron. And what is the name of this new orbital? It's not an s orbital anymore. It's not a p orbital anymore because they fused. So now it's going to be a hybrid of something in between. And here's how you figure out what it is. If we had one s, one p, a second p, and a third p, think of this as the orbitals are multiplying. They're multiplied together. So s times p times p times p. Isn't that the same thing as saying sp cubed? And sp cubed is written as sp cubed, or sp3. So that's how you get the sp3 hybrid orbital. If you're looking at a molecule and you're trying to determine what is the hybridization, here's what you do. You ask yourself how many groups had to fuse, or how many orbitals had to fuse to give me this number of groups. If we look back at the example over here, we have methane. It has 1 hybrid, a second, a third, and a fourth. You see this on an exam. Here's how you count. 1, 2, 3, 4, and then you just start filling in SP, P. That has to be SP3. So now I have a question for you. Do the hybrid orbitals have to hold a bond, or can they hold a lone pair? Let's see, I'm seeing, is the lone pair stable alone? Yes, we're assuming that the molecule has a lone pair. So for example, if we're looking at water, water has an oxygen bound to 2 hydrogen atoms, but to have a complete octet, it has to have 2 lone pairs. If you look at oxygen, what is the electron configuration of oxygen? So let's take a look. Oxygen is number 6. The 2 are in the kernel, or we can say there are 6 valence electrons. So you write it out that oxygen is equal to 1s2, 2s2, 2p4. 2 and 4 is 6. if you set it up, you'll notice that the s orbital has 2 electrons, and the p orbital has 1, 2, 3, 4, with 2 capable bonding positions. Now this is a little bit tricky because it looks like oxygen is happy to bond as it is. Now this should have been lower. It looks like oxygen is happy to bond the way it is now, but lone pairs have to have the same energy level as a bond. So even though it doesn't look like it wants to hybridize, it will. So these will jump up. The electrons will stay where they are, but they'll now be hybrids that have the same energy level, and it'll still form an sp3 hybrid. So it'll still form an sp3 hybrid, and if you look at the water molecule, just imagine that instead of oxygen having 2 lone pairs, it has a bond, but that bond is just holding 2 electrons. And if you think of it that way, you'll be able to easily identify hybridization regardless of bonds or lone pairs on the molecule. So yes, H2O, the oxygen is sp3 hybridized. Hydrogen is not hybridized. Hydrogen is just S, because hydrogen doesn't have any p orbitals to fuse. Oxygen is going to be sp3. So now let's take the same idea and take a look at what happens if I try to put a pi bond into the molecule. Anyone know the name of this molecule right here? While you type the name in, let's take a look at carbon first. We have the s orbital with 2 electrons. We have the p orbital with 2 electrons as well. But in this case, we need to have a pi bond. What is the hybridization of the pi bond in any molecule? While I do that, I'm just going to move the electrons over. Remember that the p orbital is x, y, and z, constantly rotating in space, so it doesn't matter where you put the electrons as long as they're facing in the same direction. For those of you who said this is formaldehyde, you are absolutely correct. So formaldehyde, or the IUPAC name, if you want to get technical, would be methanal, because it's meth for one and al for an aldehyde. In order to form a pi bond, I need to have the electron in its initial unhybridized state. So that means if I want a pi bond, I need to save a p electron. Save 1 p electron for a pi bond. We save that p electron, and then we use the rest of the orbitals to fuse together and form something that's degenerate. So this time I'm going to fuse s and only 2p, and that'll give me a new hybrid made up of s plus p, which is sp squared, or sp2. So carbon here is sp2 hybridized, and the pi bond is formed with a p orbital overlap, and the pi bond is not hybridized. What do you think the hybridization is going to be for the oxygen atom? Just like carbon, oxygen is also sp2 hybridized. How do you recognize it? It has 1 attached group, 2 attached groups, 3 attached groups, and all you do is count. 1, 2, 3, spp. And you know it's sp2. All right, so let's take a look now at a triple bond. Let's say I want to form the molecule hydrogen cyanide, HCN, and I want to look at the carbon atom. Notice that there is 1 single and 2 pi bonds. So when I write that out, looking at the configuration for carbon, we have S, 2 electrons, P has 2 electrons, I'll keep them both to the right, but now I need to save 2. Save 2p for 2 pi. That means that if I were to fuse the remaining orbitals, if I take s and I elevate it, and then I fuse it with that empty p orbital, now we only have 1 s and 1 p for an sp hybrid. 1, 2, sp. What is the hybridization of the nitrogen atom directly near the carbon? The nitrogen is also sp hybridized. It has 1 group, which is a lone pair, another group, which is this entire thing, and that means they are both going to be sp hybridized. Another trick you want to consider, for triple bound atoms, If something is triple bound, if one is sp, the other one is likely sp. But for something that is double bound, don't fall for it because they're not always going to be the same. So for example, if I give you the molecule CO2, carbon dioxide, what is the hybridization of each atom on the CO2 molecule? We'll look at the Lewis structure in a minute on how to come up with it, but the Lewis structure for CO2 drawn out gives you a carbon with a double bond to 2 oxygen atoms, and each oxygen has 2 lone pairs. So if we want to look at the hybridization, let's start with carbon. Carbon has 2 groups attached, 1, 2, sp, and it's not a triple bond, but it's still 2 pi bonds. 1 pi bond to each of 2 separate oxygen atoms. So that's sp. And then if we look at oxygen, oxygen has 1, 2, 3. So that's 3 groups, 1, 2, 3, spp or sp2. And the same thing on the other side, sp2. So the oxygens are sp2, even though they're attached to carbon, carbon is not sp2 because it has pi bonds in each direction. Question, I don't understand the P overlap. Let's take a look at the idea of a pi bond. We had acetone, now I'm saying acetone. We had formaldehyde earlier that looked like this. If we want this to be acetone, by the way, you just make that a CH3, CH3. Now we have acetone. But let's go with formaldehyde because it's easier to work with. Let's tip this molecule sideways, so we'll sort of drop it on its head and put the carbon, oxygen, hydrogen, and hydrogen. Now a pi bond is flat, so let's look at it from the side. If we actually, let's go back and discuss that real quick. We'll get back here in a moment. If we have something that is sp3 hybridized, then you have to keep in mind the VSEPR theory. Again, something you learned in Gen Chem. VSEPR stands for valence shell electron pair repulsion. So let's write it over here. Valence shell electron pair repulsion. What does that tell you? The VSEPR theory tells you that the atoms are going to, or not the atoms, the electrons, are going to push the other ones as far away as they can because negative repels negative. So when you have 4 bonds on an atom, they're going to try to get as far away from each other as possible, and the furthest they can get on something that is sp3 hybridized is going to be 109.5 degrees. So if you see an sp3 hybrid, recognize that it'll be 109.5 degrees, and the shape is going to be tetrahedral. Tetrahedral is the electronic configuration. If you have lone pairs instead of atoms, the angle would change slightly, but it'll still be very, very close to 109.5. But then if we move on to something that is sp2 hybridized, now you only have 3 groups. What is the farthest that 3 groups can push each other away? Well, if you have a circle and the central atom is in the middle, a circle is 360 degrees. Slice it into 3, and that means you get a 120 degrees trigonal planar. Trigonal planar is trig or tri for 3. Planar is in one plane. That's how your textbook's going to use it. That's how your professor's going to say it. I'm going to call it by what it is. It's flat. And if you can understand that sp2 hybrids are flat, that'll make a lot of the reactions make sense, especially when you're trying to understand the stereochemistry of the reaction. So if something is sp2, it'll be trigonal planar, flat, and approximately 120 degrees. If it's all the same, it'll be 120. If you have some atoms and some lone pairs, the angle will change slightly. And then we get to sp. Well, what is the absolute farthest that 2 groups can be from each other? 180 degrees. So this will be 180 degrees, and the shape is linear. And it's very easy to see that it's just one straight line. So going back to our example here, this is flat, so I want to look at it from the side, and I want you to see it almost as if the 2 hydrogens are blocking each other from view. So that you have a hydrogen in the back, a hydrogen in the front, and that bond is going into the page. This bond is coming at you out of the page. But the 2 atoms here are just overlapping like that. The same idea is going to happen here though. Sorry, this should be coming out of the page. Here you have something going into the page. And what is it? Lone pair of electrons. But now you have a p orbital that sits very high and very low on the atom. You have an electron in the p orbital, and what they're going to do is bond with each other. They bond at the top. The negative space, the empty space, will bond at the bottom. Sometimes you'll see it as shaded or unshaded. It's just the two nodes of the p orbital. And when they overlap, what you get is something that looks like this. That's the top. That's the bottom. I'm not very good at drawing these, but the idea is that this is your pi bond, and the pi bond sits very high and very low on that flat molecule. You guys are putting my lack of drawing to the test. So, okay, yes, I'll go ahead and draw what the sp looks like. I'm going to try very hard to make it look realistic. We had HCN, so we'll have a hydrogen with an s orbital bound to a carbon with an sp orbital that is bound to the nitrogen that is also with an sp orbital, like that, and nitrogen has a lone pair sitting over here. There are two pi bonds. One of them is going to sit in the up-down, so that'll be the y-plane. So we'll show the pi bond like this. And the other one is going to sit in the z-plane. One half is coming forward and the other half is going back. So that's going to look like this. This one's coming forward, and then half of it, let's show the going back in a different color. That's going back, and this part's coming forward. So that right there is going to overlap in the back. This is going to overlap in the front, and that right there, as we said, is in the z-plane. This here is in the y-plane, and these are your two pi bonds. So we'll call it pi y and pi z. All right, so now that you get the concepts, let's tie it up with a little bit of a trick. If you want to put this on a flashcard, study it. Don't just memorize it. Make sure that you understand what's going on. But first we have a question. The green and purple's in the x-plane. Yes, this is just in the plane, and then the pi bond in the y direction is up and down. Z direction is forward and back. So I said that if we have something that is sp3 hybridized, then the bond angle should be 109.5. The three different angles that you probably may have to memorize are going to be when you have, let's take a look. I'm just trying to think of how to set up the table. So sp3, you know, is going to have 4 groups, right? If it's 4 groups, sp-p-p, that's sp3. The number of pi bonds is going to be a giveaway when you have your sp and your sp2, especially when you're in line structure and you can't tell what's going on with a molecule. In this case, we have none. But within the 4 groups, the question is how many are lone pairs? Lone pairs. So if we have 0, 1, or 2, I'll put an example. Something like CH4 has no lone pairs, NH3 has 1, H2O has 2. Then what we're looking at for the bond angle is 109.5 for just when they're all the same. That one lone pair shrinks it a little, so it's about 107 degrees. The H2O has 2 lone pairs, shrinks it even more. I think it's like 105, and I know that some of your professors are going to ask you to memorize it. And then the shape, in case you have to know, it's going to be tetrahedral or a tetrahedron. Same thing, one's a verb, one's an adjective, sorry, and one's a noun. This one is going to be trigonal pyramidal. Again, it's a Gen Chem topic. I'm just giving you a quick refresher. And this one is simply bent. If you're looking at something that is sp2 hybridized, your clue is 3 groups. That is your absolute dead giveaway, or 1 pi bond. So that's what you want to look for. What would be an example of 3 groups without a pi bond? So if it's carbon with 0 pi bonds, it's a carbocation. That's the trick that I want you to recognize. So if you see a carbocation and you count the 3 groups, that's how you know it's sp2 hybridized. The bond angle is going to be 120 degrees, and the shape we said is trigonal planar. Look at the difference between trigonal pyramidal, when you have an extra lone pair pushing on those bonds, versus trigonal planar when it's just 3 groups. Question, is that molecular shape or geometrical? Shape and geometry are the same thing. So you're looking at the molecular geometry versus the electronic geometry. These are your molecular geometries. If it's electronic, you're always looking at the one that has no lone pairs. If it has no lone pairs, it's in its truest form at its electronic geometry. Okay, and then the clue for SP is the fact that you have only 2 groups or 2 pi bonds, and that's why something like carbon dioxide is not a triple bond on the carbon, but it's 2 pi bonds, 1 in each direction. Bond angle is 180 degrees, and the shape is linear. Knowing the hybridization, knowing how to calculate, knowing that table that I just showed you is very helpful. But what if your professor does something like this and tells you identify the hybridization of every single atom on the molecule? And you look at this and you say, okay, Leah said if it has 4 groups, it's sp3, but this one right here, it's a carbon atom, and it only has 1 group. So what's the hybridization? Well, that's a methyl group, isn't it? Isn't that really a line structure for CH3? So what do? Do you take the time to write everything out, especially if it's a multiple choice exam and you only have a few seconds? The answer is no, absolutely not. Remember, I give you 2 different things to look for. The 2 different things, the groups or the number of pi bonds. And when you're faced with a molecule like this, use the number of pi bonds to figure out what they are. I like to go from SP to SP2 to SP3. Actually, let's do them in different colors. And the reason for that is SP and SP2 are the easiest to identify. SP3 will just be, by the way, everything else that's left over. So who wants to see this solved in less than 30 seconds? All right, let's give it a shot. SP, we're looking for triple bonds, or 2 pi. Not a single atom here has 2 pi bonds on the same atom. We have 0. SP2, we're looking for pi bonds. 1, 2, 3, 4, 5, 6, 7, 8. And here's the trick. Nitrogen near an sp2 carbon is going to hybridize so that it can resonate and resonate. So that means I totally lost count. 6, 7, 8, 9. Oh, whoops, that's not 9, it's 10 because we have an oxygen here that is also capable of resonating. Anything that's left, if it's not a hydrogen, is going to be